Hi folks, welcome back to another YouTube live session. As always, there's going to be a chat box on the right hand side that you can always type your questions into. So without further ado, we're going to get started, and let me know if you have any questions along the way. And where we're going to begin is sequences. So we're going to determine if these following sequences converge or diverge. So when looking at this, we're going to start with an equals arctan of 3n. So all this thing is doing, when you're trying to determine if it's convergent or divergent, you're just taking a look at the limit as n goes to infinity of whatever your sequence is, assuming it's turned in terms of n here. So this is limit as n goes to infinity of arctangent. Now we'll have a 3n we might be concerned about, but it's really not a big deal. We'll be able to solve that too. So first off, we'll kind of explain what happens with the arctangent. So the tangent function, when you take a look at it, it looks something like this, where you have bounds at negative pi over 2 and pi over 2, and then we repeat this over and over and over again. And so you can do this infinitely many times. Now what we do oftentimes is we say, okay, we need this to be one-to-one to talk about an inverse function. So we cross off this one and this one. The only one we leave is the bounds between negative pi over 2 and pi over 2. And this allows us to look at the inverse function. And so when looking at the inverse function, what do we actually have? Well, you reflect over the line y equals x, and what that does is it switches the roles of x and y. So notice we had a vertical asymptote at x equals negative pi over 2 and pi over 2, so that means now we have horizontal asymptotes at pi over 2 and negative pi over 2. And the graph, as I mentioned, just kind of reverses roles with your x's and y's, so it looks kind of like the same graph just flipped on its side. And that's the whole idea here. Okay, so this is y equals arctangent of x. Okay, so now that we have that graph in play here, we have a pretty good idea as to what happens. As you know, notice that's 3 or x, and this is going to be 3n. But the nice part is we can take, since arctangent is a continuous function, we can take that limit to the inside. So you get limit as n goes to infinity of 3n. And that inside is going to infinity. But notice, as we go to infinity, what are we approaching? Well, we're getting closer and closer to this horizontal asymptote of pi over 2. So the whole answer here is just pi over 2. So what we have is this thing converges to pi over 2. And that's a whole bunch of what we're doing with sequences. We're just trying to determine where's the limit as n goes to infinity. And we do that over and over and over again. Okay? So keep that in mind when we move on to the next one. Okay, so with the next one, we got a little bit of work to do actually. So the first bit, we have bn equals 1 over n cubed plus 4 over n cubed plus 9 over n cubed plus yada 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 all the way to n squared over n cubed. Okay, so when taking a look at this one, what actually happens? Well, we can rewrite this. So bn equals, since it's a common denominator, well, let's try and rewrite this. This is 1 plus 4 plus 9 plus so on and so forth, all the way up to n squared, all over n cubed. Now, looking at this, we know what this sum is up top in the numerator. That sum can be rewritten as just n times n plus 1 times 2n plus 1 all over 6. Okay, so that's the whole numerator there. And where that came from in Calc 1, you had this formula that said, hey, you know what, we'll give a few of them here. So you have the sum I equals 1 to n of I was n times n plus 1 all over 2. You probably dealt with that in Riemann sums. And then you had the one we're getting at right here, sum I equals 1 to n of I squared. that was n times n plus 1 times 2n plus 1, all divided by 6. So that's where that formula came from. Now, so what this means is when we trying to determine if this thing converges or diverges, we're taking the limit as n goes to infinity. We'll do a little simplifying. So we'll go n times n plus 1 times 2n plus 1 all over 6n cubed, but I'm going to write n cubed slightly different. 6n times n times n. And the reason why is just to make our lives a little easier. We can pull out the 1/6. You can do limit as n goes to infinity of n over n. Then you can do another limit as n goes to infinity of n plus 1 over n. And you could do another limit as n goes to infinity of 2n plus 1 over n. Okay, so what does this do? Well, taking a look, this piece right here, that limit as n goes to infinity, is going to be 1. The second piece, you could use L'Hopital's rule or just recognize the powers. That's going to be 1 as well. And this last piece will be 2. You can use L'Hopital's rule or whatever the case may be. So we get 1/6 times 1 times 1 times 2, which is just 1/3. So our solution here is it converges to 1/3. And we are done. Okay, any questions on that piece right there? Also, since I don't see any questions, we'll keep on moving on. And once again, there's a chat box over on the right hand side. If you've got questions, let me know. So going back to series, let's try and see how these series work out. So series is basically a sequence of what we call partial sums. Okay, now what do I mean by that? Well, let's take a look at this thing. And what I'm going to do is I'm going to write out a few terms. So notice that when we start at n equals 1, we get sine of 2 minus sine of 2 over 2 plus, okay, so now what's our next term? Well, we'd be at n equals 2. So when we plug in n equals 2, you get sine of 2 over 2 minus sine of 2 over 3. Well, what's our next term? Well, we'd start at n equals 3, and you get sine of 2 over 3 minus sine of 2 over 4. And we continue with this trend. Okay? And what actually happens is, when you take a look at this a little closer, you have negative sine of 2 over 2, you have positive sine of 2 over 2. So those two things cancel. You have negative sine of 2 over 3, you have positive sine of 2 over 3, so those things cancel. Okay? And we can continue to do this over and over again. And so what happens is we try and form a sequence of what we call partial sums. So what is a partial sum? So Sn equals, basically it's the first term of the sequence, because this whole thing right here is a sequence. So we take the first term plus the second term plus the third term plus so on and so forth all the way up to the nth term. Right? And so now what we are going to be able to do is hopefully come up with some sort of formula. So notice we get A1, A2, A3 are listed up above. So we can write this as, once again, sine of 2 minus sine of, I'll write it as sine of 1, just to shorthand it. And then the next one was sine of 1 minus sine of 2/3. And then we go plus, and then we have sine of 2/3 minus sine of 1/2. And we continue in this trend until we finish with the nth term, which would be sine of 2 over n minus sine of 2 over n plus 1. Okay, so now what happens? Well, let's take a look. The sines of 1s, they cancel, just as we said before. The sine of 2/3 would cancel. Now what about the sine of 1/2? Well, when you take a look at sine of 1/2, the next term on down the sequence would be, you'd have plus sine of 1/2, because it'd be sine of 2 over 4, and then minus sine of 2/5, so on and so forth, right? So that's going to cancel. Also, the sine of 2n, the previous term right before in this direction, would be sine of 2 over n. But the 2 over n plus 1 is left alone. So a simplified format for these partial sums is just sine of 2 minus sine of 2 over n plus 1. So determining if this series converges is the same thing as us determining if this partial sum converges. So we take the limit as n goes to infinity of Sn, and so we get the limit as n goes to infinity of sine of 2, which is just a constant, so we don't have to worry about that, minus sine of 2 over n plus 1. Okay, so where do we go from here? Well, limit as n goes to infinity, this whole shindig right here goes to 0. So we have sine of 2 minus sine of 0, which equals just sine of 2. So this thing, notice we aren't looking at the a sub n's at this point, we are looking at the s sub n's. So what we can say is not only that this thing converges, which a lot of times it'll take more work, but this thing converges to sine of 2. Okay, that's kind of a cool result that you get into. And this actual series is given a special name. It's called a telescoping series. Why is it called a telescoping series? Well, basically you have this addition and subtraction kind of canceling each other out. So you start with the first part and you end at the end, right? You can always go to the very end and kind of see what's left there. And that's the limit you're going to take. So the next one, just so we can see the telescoping series at play one more time, we have a similar thing going on here. So we start at n equals 0 though now. So when we plug in 0, we get e to the 0 minus e to the 7th, right, when we plug in 0 for that second term. And then we get plus, it goes e to the 7th minus e to the 14th plus e to the 14th minus e to the 21st plus e to the 21st, and I'll write down the next one just for kicks, e to the 28th, and then we continue that trend. Well, notice the 7ths will cancel out, e to the 7ths will cancel out, the e to the 14ths will cancel, the e to the 21st will cancel, e to the 28th will cancel with the next term. So the way we can approach this one, same way, you're having a whole bunch of stuff cancel, right? Now, I should give a warning too. You notice how things are canceling nicely and we will have an nth term involved. That's something that we want to take note of here. So if we have a1 plus a2 Sn is that nth partial sum. So you sum this up all the way to an. What do we get? Well, we get, so you get e to the 0 minus e to the 7th. That's a1 plus, here's a2, e to the 7th minus e to the 14th. So we just plugged in 2 for the ends. Or, I'm sorry, this was a0. I should clarify in this case. a0, a1 plus a2 plus so on and so forth all the way up to n. Why a0 to start? Well, you'd have an s0, and so you have s0 was a0, s1 was a0 plus a1, so on and so forth. It's because we're starting our terms at n equals 0. So this is a0, my apologies there, a1 plus, here's a2, e to the 14th minus e to the 21st, and then we keep on going on down the line until all of a sudden, what do we end with? Well, we're going to end with e to the 7n minus e to the 7 20n plus 1. So what happens now? Well, the e to the 0 you're left with. You have e to the 7's cancel, e to the 14's cancel. Your e to the 21, we already saw that's going to cancel with the next term. E to the 7n, the previous term is going to have that. So that one's gone. So what are we left with? Well, Sn would be equal to e to the 0 minus e to the 7 quantity n plus 1. Okay, so when we take the limit as n goes to infinity of this thing, e to the 0, which is actually just 1, so I don't have to write e to the 0 every time, but the second part is going to infinity. So what that means is this thing, we have a negative symbol in front, so this is negative infinity, is what that whole thing becomes. So this thing diverges, right? So you have cases where telescoping series can converge, in cases where they can diverge. Okay? So yeah, keep that in mind at the end of the day, and you can see how those go. Now there will be some shortcuts to how we solve some of these, and we'll talk about some of those coming up here real soon. So in this case, we have 1 minus 1/3 plus 1/9. Whoops. Oh, there we go. Back on. Okay, so 1 minus 1/3 plus 1/9 minus 1/27. What does this thing equal? Well, we have a summation. Notice it looks like we're taking 3 to the n in the denominator, so we'll have a 1 over, and then it seems like 3 to the n. Okay, and we'll take our sum from n equals 0, because that way we start at 1, to infinity. Now the only thing we have to do is alternate the negative business. So notice this can become negative 1 to the n, 3 to the n. So another way we can write this is, if you like, we could write this sum n equals 0 to infinity. Notice the n powers are the same, so we can get away with this. You can write this as negative 1/3 raised to the n. Same song and dance. So recall that this is one of those summations. You have a times r to the n, and when this n equals 0, right? Otherwise, if n equals 1, you might have an ar to the minus 1 formula. But when this equals 0, this is a over 1 minus r if the absolute value of r is less than 1. Well, notice the absolute value of r is less than 1. So, by the way, this is called a geometric series. Okay, so if this is a geometric series, what do we have here? Well, there is no a value, it's just 1 because we already have the r to the m. So r equals negative 1/3, and we're going to plug that into our formula. So notice we get the summation n equals 0 to infinity of negative 1/3 to the n. That should equal 1 over 1 minus negative 1/3. And so this thing equals 1 over 4/3, which is equal to 3 over 4. So what that tells us is this is, and we actually had it before, as soon as we saw r satisfied that absolute value of r is less than 1, we knew this was a convergent geometric series. Okay, so keeping that in mind, notice we have something else that also looks like a geometric series, because once again our exponent is where our variable appears. The big difference here is n equals 1. So when we start our summation at n equals 1 to infinity, that means if we have a times r to the n minus 1 power, that's when we have a over 1 minus r, if r, the absolute value of r, is less than 1. Okay. So taking a look at this now, oh, I'm glad to have you here, Chelsea, so that's good. If you have questions, just ask along the way, so as always. This one you can actually break up a little bit nicer. So sum n equals 1 to infinity. We can write this as 2/11 to the n plus, in another summation, n equals 1 to infinity of 8/11 raised to the n power. And that's just properties of sum. The order in which we add things is not going to make a difference, right? So that's why we can get away with that. Now that's different than if we had two sums back to back or something like that, where we had two summation symbols. But since they're a plus in between, we can just break this up as you see here. Now what happens? Well, we need it in the form to the n minus 1. Well, there's an easy fix for that too. So we can pull out a factor of 2/11. So if you pull out a factor of 2/11, that leaves us with 2/11 to the n minus 1. And the reason why is you actually have, you add, this is 2/11 to the first power, and you add that to the n minus 1 power. So you get n minus 1 plus 1, that would make nth power. So we basically just rewrote that original summation in a slightly different format. And the same song and dance applies to the next bit. So we can pull out an 8/11, and then we'll have an 8/11 to the n minus 1. So at the end of the day, what do we have our summation being equal to? So I'll write the original here, and then we'll just apply what we see in this next case. So what that means is that we have an A here and an R here. Okay, so if that's the case, we have A, which is 2/11, and then it goes 1 minus R, which is also 2/11 in that first case, plus A is, in the second case, let's see, we have this being A and this being R, so there's not much trickiness going on here. This is 1 minus 8/11 down below. And an easy way for us to kind of solve this, you can bring the 11 on down. So you get 2, and then you get 11 minus 2, and then plus 8, and then you get 11 minus 8. Okay, so this becomes 2/9 plus 8/3. Ooh. Okay, so 8/3 would be 24/9, and so that would make it, I believe, 26/9 is our final solution. That means that this series converges to 26/9, and then I'll put it's a geometric series. And the beauty with the geometric series, it cuts down our time versus like where we had the telescoping series, we had to do this sum back and forth and kind of figure out where it goes. Geometric series and a lot of these other tests are going to be cutting down time. And the main thing that we're going to be looking for is whether things are convergent or divergent. So keep that in mind at the end of the day too. So we want to determine if this is actually summation is actually convergent or divergent. There's a couple different ways to approach this thing. So when looking at this one, you can actually take and use an integral test, because you have this as continuous, it's positive, and it's decreasing for the given interval. I'm going to show you using the integral test, but then I'll show you a much easier way to kind of approach this thing. So the integral test. So I'm kind of glossing over the fact that it's continuous, positive, decreasing, but that's something that you need in order to use the integral test, so keep that in mind. Now, the integral test is basically, let's, instead of you seeing the summation, let's turn it into an integral. So, and then we'll change all the n's to x's. So we're going to go from 2 to infinity of 1 over 7x minus 2 raised to the 7th power. Okay, then we have a dx. So notice in this case, this becomes the integral from, let's see here, we go from 2 to t, and we need a limit as t approaches infinity of 1 over 7x minus 2 raised to the 7th power dx. Okay, so using that idea, yeah, so I'm doing, am I just doing a basic review module? Yeah, I'm going to kind of try and touch on, okay, here's all the series, here's the sequences, and here's a whole bunch of other pieces and components that we can tie in. I'm going to try and build to absolute convergence, and along with that, conditional convergence. Okay, sorry for the buffering issues. Let's get back to it then. So in terms of what I was saying, yeah, we did have absolute convergence, conditional convergence, and things like that are going to be what I'm going to finish with, and possibly show a how we do an approximation in an alternating series or something like that. So when we take a look at this stuff, so trying to make sure we get it down and whatnot, yeah, I could hear your, oh yeah, I apologize for hearing the children in the background. It's bedtime, so we're kind of multitasking here. So yeah, taking a look from here, where do we go? Well, you have this 1 over 7x minus 2 raised to the 7th power. If we're going to integrate that, what we need to use is a u substitution, so I'll do that separately. 1 over 7x minus 2 raised to the 7th power. And then if we let u, oh, and I have a dx going on up here, u equal to 7x minus 2 du equals 7 dx. So du over 7 equals dx. So this integral becomes the integral of, we have 1/7 du over u to the 7th. And so from there, this is u to the -7 essentially. So you can just kind of take that, I'll pull the 1/7 out in front. You could write u to the -7 du. And so this becomes 1/7 times -1/6, and then it becomes u to the -6 du, or no longer du, my apologies, plus a c. And you can see that this becomes, whoops, we can make this -1 over 42, and then this is, well, we can put the u to the 6 down below too, plus c, and that is the same thing as -1 over 42 times 7x minus 2 raised to the 6th. Okay, plus some constant c, which we'll not worry about here in this next step, because what this equals is the limit as t approaches infinity, and now we have -1 over 42 and times the quantity 7x minus 2 raised to the 6th, evaluated at 2 and t. Okay, so in that case, what happens? Well, as t goes to infinity, well, here, actually, let me plug it in first. And you'll see, hopefully quickly enough, why actually we don't prefer this method. Limit as t approaches infinity of -1 over 42 7t minus 2, the quantity raised to the 6, minus a minus makes a plus, so we'll have 1 over 42, and then when we plug in 2, we'll get 14 minus 2, which is 12 raised to the 6. Okay, so this whole thing, though, it shoots off to 0. So our final answer is 1 over 42 times 12 raised to the 6th power. So this tells us it converges by the integral test, which is quite a bit of work for that result. And so what happens oftentimes is, well, there will be occasions we have to use the integral test, but a lot of times, and same thing when we were talking about in improper integrals, the comparison theorem. Well, now we have that comparison test, and that will do us wonders here, and I'll kind of explain why. So in the comparison test, let's compare two things. So first off, if I did for n greater than or equal to 2, if we compared 7n minus 2 and let's say n, which one's larger? Right? So for n equal 2, you can see that the left hand side is 12 and the other side is just 2, right? Then when you go n equal 3, you're just getting larger and larger by the multiple, so this is obviously larger in that case. Well, now that means also, since we're also bigger than 1 in those cases for n greater than or equal to 2, 7n minus 2 raised to the 6th power is going to be greater than or equal to n to the 6th. Oops, I'm sorry, not to the 6th. Let's go to the 7th. And these are all positive numbers, right, for n greater than or equal to 2. So what this means, now if we turn this around, we have 1 over 7n minus 2 raised to the 7th is less than or equal to 1 over n to the 7th for n greater than or equal to 2. So what does that do? Well, the big result here is, notice the summation n equals 2 to infinity of 1 over n to the 7th. This is a convergent p-series. With p equals 7. Okay, so we have the larger series is convergent. By the comparison test, the smaller series is convergent. So hence, summation n equals 2 to infinity of 1 over 7n minus 2 raised to the 7th is convergent by the comparison test. By the way, you could also use limit comparison test. That would do the same thing. You're just taking the ratio of the two, so 1 over n to the 7th and 1 over 7n minus 2 raised to the 7th. You will find that the limit as n goes to infinity of those two would be either 7 or 1/7, depending upon which one you had on top. But that's good enough for us, so we can use the limit comparison test, and also since that one is actually a p-series with p equals 7, we'd be done that way. So there's multiple ways. What I would suggest, there's no calculations really involved when we're using the comparison test here. It's the real calculation is in terms of trying to find the inequality that satisfies it. So that's why it's so important to know the comparison test and the limit comparison test. They can do wonders for you in terms of cutting down time too. So let's take a look at this next one. We have a summation n equals 1 to infinity of 9n to the 6th over n to the 7th plus 8. Any guesses as to what might be a good approach on this one? So what should we use? Should we use an integral test? Should we use a comparison test, limit comparison? What's probably the best bet in this one? And if it was me, I'll be honest, what I kind of look for in these problems is I try and look at these powers and kind of get the behavior of what this thing's going to look like. And usually my own personal preference would be a limit comparison between the three. I find the limits to be easy. That might not be the case for you. So whatever works for you the most would be the big thing. Yeah, so you're ahead of me on the ratio test. The interesting thing here, though, I don't think the ratio test would work. And I can show you that real quick. So the ratio test says, hey, we need to look at a sub n plus 1 over a sub n, I believe, right? And if we did do a ratio test, so a sub n equals 9n to the 6th over n to the 7th plus 8. Now I'm glad we're mentioning the ratio. You couldn't do a ratio, and so yeah, that's a great question, and so I'm going to kind of show you what happens. There's going to be certain ones where we're going to need to use other things in there. So a sub n plus 1 equals 9n plus 1 raised to the 6th all over n plus 1 to the 7th plus 8. So when we do this, we get m plus 1 to the, 9n plus 1 raised to the 6th power all over m plus 1 to the 7th plus 8. And the absolute value, notice that's not going to make much of a difference here, just because of the fact everything's positive already. And then over in the bottom we got 9n to the 6th. And we have an n to the 7th plus 8. Okay, so, let me fit in a limit as n goes to infinity here. So breaking this up into the parts that are needing it to be broken up into, you have the limit as n goes to infinity. We'll break it up into two different limits. You get 9 n plus 1 to the 6th over 9n to the 6th, and so that'll be a little bit easier for us to take the limit. And then in the second case, you get limit as n goes to infinity, and we'll have, what do we have, n plus 1 to the 7th plus 8 over n to the 7th plus 8. Now let me know, how good are you at limits too? That's what I'm kind of here for. If you want, we can go through quick. If not, we can go through all the extra steps to kind of get there. In the first case though, I will make it a little bit quicker than what the second case with that plus 8. That's going to be a little bit more tedious. So what happens is, if you take a look, we have the 9s will cancel immediately in that first limit, and so what we're left with is we can pull the limit to the inside because we don't have, it's a constant on the outside. So you have n plus 1 all over n, and then that's raised to the 6th power. Okay. So in the second case, what do we have? Well, this is a little bit trickier. So what we can do, there's a couple ways. You could do L'Hopital's rule multiple times. But an easier way would be to divide both numerator and denominator by n plus 1 to the 7th. And what would happen if you did that is you get 1 plus 8 over n plus 1 to the 7th. And then you'd have n over n plus 1 raised to the 7th, because both of those are the same power, plus 8 over n plus 1 to the 7th. So looking at this thing's, you go, this is going to 0, this is going to 0, and so you have the first case, this is going to be 1 to the 6th times, you have 1 over, this is going to be 1 to the 7th. Okay, so this is 1 times 1, which equals 1. This is inconclusive in the ratio test. You need either something greater than 1 or less than 1. Right? And by the way, the ratio test, if it's greater than 1, you're going to have that as divergent. Basically, you're saying in that case, the next term is increasing compared to the previous term. So you're increasing, that means you're never going to end up getting back to, you want this thing to be approaching 0 essentially. So since it's increasing slightly, you're going to have a divergent in that case. If it's between 0 and 1, and the reason why I say between 0 and 1, because it can't be negative, we're taking an absolute value. So in that case, if it's between 0 and 1, then you're going to get convergent. So those are the tricks to those problems. Now, equal 1, we don't have a solution for that case. So we're going to have to use another method. And that's why it goes back to integral test or comparison test or limit comparison test. Any questions on that as I'm erasing it here, I guess? If there are questions, let me know. Yeah, that's right. So it is a weird rule with 1, most definitely. So the ratio and the root test, if it equals 1, you don't have a solution. But it's kind of the opposite of the limit comparison test. So if you use the limit comparison test, 1 is a good number for us. So, but the ratio and the root test are the big ones to know. But what happens is the same thing with L'Hopital's rule too. People get a little bit happy with it, think it works everywhere, and it doesn't. And this is a case where you actually have to use a different rule. So yeah, there's going to be a 2-minute delay actually. So I'm seeing the results after that little setback in the stream health. It bumped me back, so I'm about a 2-minute delay or so, or maybe even a little bit longer on your end. So yeah, don't worry, I can wait. So just keep on asking questions along the way. Now moving forward, what's happening here? Well, let's try and use, in this case, a limit comparison test. Okay, and what do we want to compare it to? Notice you have n to the 6th and n to the 7th. Let's compare this thing to the summation n equals 1 to infinity of just 1 over n. Okay, and then so let's call this, well, whatever we want to call it. So at the end of the day, what we need to do is compare the terms. So you take limit as n goes to infinity of, we'll take the top one, 9n to the 6th over n to the 7th plus 8. And then the bottom one will be 1 over n. And since we're dividing by a fraction, we multiply by its reciprocal. And we get limit as n goes to infinity, the 1 over n goes up top. And so we get 9n to the 7th. And then we have an n to the 7th plus 8. So, oh, I just see another one. Yeah, so convergent and divergent are the opposite of the p-series too. Yeah, so that's right. It does get confusing with the p-series. The big ones are going to be like the 1 over n. You're going to see this pop up quite a bit. And it's a p-series in some regards, but it's actually given a special name because it happens so often. This one is our harmonic series. And I'll let you decide, is this a convergent or divergent harmonic series? So if you take a look, we have the 9n to the 7th and an n to the 7th plus 8. What's the limit? You can use L'Hopital's rule if you want, but actually just notice the degrees of these polynomials are the same, so you just take the coefficients in front. So this just becomes 9 over 1, which equals 9. Done. Right? So this means we can use the limit comparison test. And then the one we were comparing it to is the divergent harmonic series. The harmonic series always diverges. This is when your power p equals 1. So that means this summation, since we just did a limit comparison, this is satisfied here. 9n to the 6th over n to the 7th plus 8 is divergent by the limit comparison test. This is always the tricky part. It's trying to figure out what sort of test do we use. You know, you keep on going through these over and over again. At the end of the day, though, you keep on practicing, you'll start to see the trend. Especially when we get to power series. Hopefully this will get a lot easier. Power series is going to be where we start defining functions in terms of series. So that's what we're gunning for later on down the road. So with this next one, we have cosine squared n, and then square root of n, and then an n to the 6th. What the heck should we use in this one? Well, this is where we want to tend to avoid the limit comparison test, and it's the reason why. If I take a limit as n goes to infinity of this thing, I really have no idea where this thing is going. So that's where you want to go back and take an integral of this. Also nasty, so that kind of leaves one sort of strategy in these cases, and it's going to be the comparison test. And you might say, oh, what about ratio test, root test, and all that stuff? Ratio test also won't work because if I have cosine squared of n plus 1, I have no idea relative to cosine squared of n where that thing is going. So the comparison test is what we'll use here, and I'll write that down. Keeping that in mind, what do we have? Well, first off, cosine squared, luckily that's always positive, so we don't have to worry about that. And then we have that this is less than or equal to 1. Okay, so when we go cosine squared of n times the square root of n, that should be less than or equal to the square root of n, because that's also positive. We're good. And then if we toss this all over an n to the 6th, that doesn't change anything. And you might say, oh, we don't know what that is, but actually we do. You can subtract exponents. Remember, this is n to the 1/2 over n to the 6th, and so this equals 1 over n to the, and let's just write it as 5.5. And luckily that one is convergent. Alexa off. Sorry about my echo deciding to play there. So we have a sum n equals 1 to infinity of 1 over n to the 5.5. This is a convergent p-series. Okay, so great question I see. While we're talking about different tests, when I see a factorial, which test should stand out again? I worked on that this week. I would say 9 times out of 10, maybe even more like 95 times out of 100 would be more accurate. You're probably going to use a ratio test in those cases. And the reason why, the factorials tend to cancel out quite frequently on a majority of those terms. So I'll try and touch on that. Just shoot me one more reminder after I get towards slide 14 or whatever. Shoot me a reminder if I don't have a factorial listed in here. I'll work one out for you and kind of show you how that works with a ratio test. We can do even one of the nastier ones where you have like an n to the nth power and stuff like that going on. That's kind of common place for a lot of this stuff. So okay, yeah, great question on that. And the reason why, I'll go through the factorial business just off on the side here real quick. So say I had an plus 1 over an, and I'm dealing with a factorial. I don't know if it's in the numerator or denominator, but let's say we end up with, at some point, n plus 1 factorial over n factorial. You might say, how do we actually go about doing this? Well, when you think of, for example, let's look at 5 factorial over 4 factorial. Notice this is 5 times 4 times 3 times 2 times 1, or I can write this as 5 times 4 factorial over 4 factorial. So we're left with something like 5. Well, the same rule applies when you have an n plus 1 factorial. So you get something like, in this case it would be n plus 1 times, well, what's the term before n plus 1? Well, you subtract 1 from that, so you get n factorial. And then you have n factorial. And so those two things would cancel. As I said, it might be in the denominator. You might have a different reversal here. But at the end of the day, you get, in this case, n plus 1. Okay? So those are kind of common ones in terms of what you'll see. I'll try and think of some others too for you along the way. So I'll kind of keep that in the back of my mind and give you some other stuff you can have pop up with the factorials. So okay, back to this problem. We had the sum n equals 1 to infinity of 1 over n to the 5.5 is a convergent p-series with p equals 5.5. Yeah. Oh, good, good, good. So you did do one on the homework, and you just wanted to ask about the factorials. Good. If you find a problem that you want me to do, just kind of toss it up here, and I'll try and give it a shot on the fly and see how it goes here in a little bit. So you can put it up, and then I'll mark it down towards the end of these sections when we get to ratio and root test and stuff like that. Yeah, in this case, we got the 5.5. This thing converges. So what we have at the end of the day is the sum n equals 1 to infinity. Since this is a smaller, right? If this was a larger series, like if all the terms were larger than that previous one, that would tell us nothing. So be careful on that. But since it's smaller and the other one's convergent, we have this thing is convergent by the comparison test. And come exam time, I will be a stickler for which tests you're using, so make sure you're labeling what tests are being used. You can notice I'm doing that over and over again. There's a reason for that. It will benefit you too later on when we get to these power series, because you're going to have to use both ratio and root tests depending upon the scenario, and then you'll have to use one of the other tests in order to finish off those problems to find these intervals where things converge. So keep that in mind as well. Now let's take a look at this next one. So we have a summation n equals 1 to infinity of natural log of n to the fourth divided by n plus 8. Okay, so one thing we haven't been doing too often, and that I might recommend here in this case, is to actually go through and make sure this thing is going to 0. I'm not saying either it will or won't, because if this isn't even, if our terms of our sequence aren't going to 0, we're running into problems right away. Okay, so in this case, if we go limit as n goes to infinity of just the terms of the sequence, so we'll go natural log of n raised to the fourth power and divided by n plus 8, and then what happens? Well, you can use L'Hopital's rule here. So this becomes limit as n goes to infinity for natural log of n, the quantity cubed, times 1 over n, all over just 1. But what we'll start to see happen here, and just to make sure, so this is 4 natural log of n, oops, the quantity cubed all over n, and we can do a similar thing. So this thing becomes, oops, limit as n goes to infinity of 12 natural log of n, the quantity squared, times 1 over n. The derivative of the bottom was 1. In the next one, what do we get? Well, get the limit as n goes to infinity, and then we'll have, well, let's write this as 12 natural log of n, quantity squared, all over n. So notice all I'm doing is I'm testing for divergence right away. Actually, you'll find that this one isn't going to give us a nice roundabout answer, but that's okay. So this is 24 natural log of n times 1 over n all over 1. You can drop that n on down, so you get 24, oops, limit as n goes to infinity, 24 natural log of n divided by n. And so this becomes, finally, we're going to be able to evaluate the limit. Limit as n goes to infinity. You get 24 times 1 over n and divided by 1. Okay? So at the end of the day, this whole thing equals 0. So that doesn't tell us if it's going to converge or diverge. So all that junk, though, look how many times we had to take that derivative over and over again. This is going to 0 very slowly, is what that's telling you. So with this going to 0 very slowly, you might have an inclination, is this thing going to converge or diverge? Because that's what series are doing. We're trying to determine, is this thing going to 0 very fast? Because that, in those cases it goes and it converges. Is this thing going to 0 very slowly, like a harmonic series where it's 1 over n? Well, in that case it actually diverges. And so, and in the cases where it doesn't go to 0 at all, obviously it diverges as well. So the ones that converge, they're very, very special sort of series. So now we might say, oh, well, that didn't quite work out, but we can fix this a little bit. So what I'm going to do is I'm going to write out the first few terms. So n equals 1, when you plug that in, you get natural log of 1, which is 0. And then the second term, natural log of 2 raised to the 4th power all over, go 2 plus 8, that's going to be 10. Plus, then the third term is where we get something kind of interesting. N equals 3 to infinity of natural log of n raised to the 4th all over n plus 8. Now, why would I even start with something like that? Well, the reason why, when you take a look at this, you can break this apart a little bit now. Now we can start to look at natural log of n raised to the 4th power. That will always be greater than 1 in this case. the reason why we couldn't get away with that all the time, because natural log of 2, natural log of e equals 1. Okay, and so when you plug in natural log of 2, that's not going to quite cut it. So, but this holds for all n greater than or equal to 3. Okay, so a little tricky case here, but we can work this out and start to make it work for us pretty nicely. So this becomes natural log of n raised to the 4th. If we divide by m plus 8 on both sides, so this thing is always going to be greater than 1 over n plus 8. Now you might say, well, what about 1 over n? Notice 1 over n would actually be larger than the 1 over n plus 8, so you can't actually compare that nicely to the other one. So what we're going to work with is this 1 over n plus 8. Now, if this thing, if we can write this as a sum, so from n equals 3 to infinity of 1 over n plus 8, if this thing diverges, then the other one must diverge. Well, how do we see if this thing diverges? Now this is where it gets a little bit tricky. You have a couple methods, and what I would recommend is use the limit comparison test. So notice the sum n equals 1 to infinity of 1 over n is the divergent harmonic series. Okay, so now let's do this. Limit as n goes to infinity of 1 over n plus 8 over 1 over n. Now, by the way, before you could have used the integral test on this other one, but you'll see how I try and avoid that as much as possible, just because one thing with mathematicians, while they think very hard, we try and be lazy in some regards in terms of not trying to overwork ourselves with the calculations. Tedious calculations get old real fast. So this thing equals 1. So what that tells us is that the summation n equals 3 to infinity of 1 over n plus 8 is a divergent by the limit comparison test. Right? And now on top of that, so that tells us, since we have that piece is divergent, the sum n equals 1 to infinity. Notice we added the n equals 3 is just added terms on there. Natural log of n raised to the 4th of all over n plus 8 is divergent by the comparison test. Whew. So that one gets kind of crazy in terms of what happens there, but really personally I kind of dig that one because you have a couple things going on at once. So kind of neat to see how that works with, you have limit comparison test and comparison test, also using the harmonic series along the way. Okay, so when you take a look at this next one, summation, we're starting at n equals 15 to infinity. We can double check to make sure that this satisfies the condition that it's always positive terms and things like that. But what should go screaming out at you if you try and work with this, what I always tell people to look at, if you see only n's, no n's in the exponents, just look at the highest degree of these. And so what we'll compare this thing to is just, well, notice you have n cubed over n to the 4th, right? And so we have the summation n equals 1 to infinity of n cubed over n to the 4th simplifies to 1 over n. Okay, we can use a limit comparison test and hopefully get there for our answer. This is once again a divergent harmonic series. Okay, so when we do this, we're going to take a look at limit as n goes to infinity of 6n cubed minus 5n squared plus 15 all over 7 plus 2n to the 4th all over this should be 1 over n. And so this equals the limit as n goes to infinity now multiply that out, we'll get 6n to the 4th minus 5n cubed plus 15n, and then you'll have 7 plus 2n to the 4th. Okay, notice the degrees. Once again, degrees of these are 4, so we look at the leading coefficients associated with those degrees. So the whole limit on this thing is just 6 over 2, which equals 3. So since that limit is not 0, oh yes. Very good. Good catch. You can shoot me an email. I'll give you extra credit for that, Chelsea. That is n equals 1. Should be n equals 15. Thank you. Thank you very much. Doesn't matter. Still a divergent harmonic series, but at the end of the day, we do need that to kind of match the bounds. That's right. That's absolutely right. Good catch. Excellent find. I had a writing error there. So in terms of what happens now, we have this equal to 3, so that means it must match whatever the series we compared it with. So that means that the summation n equals 15 to infinity of 6n cubed minus 5n squared plus 15 over 7 plus 2n to the 4th is divergent by the limit comparison test. Now, I chose all these pretty specifically because if you tried to actually work these out with the ratio test or root test, you wouldn't get anywhere. So, yeah, and I'm glad you checked. That was perfect. The n equals 15, that's right on the money. And so just, as I said, shoot me an email. You catch a mistake I make on these, you get extra credit at any point in time. So, alright, so taking a look at that, does hopefully the limit comparison test, understanding why it is that, that makes sense. And so what we'll do is we'll keep on chugging along. Okay, so our next one, notice this arctangent of n makes a comeback here. And so if this is the case, then what happens? Well, I kind of led into this a little while ago. Notice the limit as n goes to infinity, we already talked about the arctangent of n. It was a sequence that we dealt with. So this thing equals pi over 2, right? And what that tells us is right out the gate, since the limit of the terms, you're adding pi over 2 infinitely many times essentially, or something very close to it. So that's obviously going to diverge, but there's a name for it. So this is divergent by the test for divergence. Okay. And now in this next one though, the limit as n goes to infinity does go to 0 because you have the n cubed down below. But we do have the arctangent of n for n equals 1 and higher. It's going to be positive, and this thing is going to be less than pi over 2. And that's quite nice because that means arctangent of n over n cubed is less than pi over 2n cubed. So what does that mean? Well, notice the summation n equals 1 to infinity of pi over 2n cubed. That might freak us out at first, but pi over 2 is just a constant. So now we can start playing with these sums. This is pi over 2 times the summation n equals 1 to infinity of 1 over n cubed. And so in that case, what is this? Well, this is a convergent p-series. Right, just because it has a constant out in front doesn't make a difference. Convergent p-series with p. So that means the summation n equals 1 to infinity of arctangent of n all over n cubed converges by the comparison test. By the way, you could have used limit comparison test, showed that that limit is pi over 2, and you're good to go in that case too. So either way will work. I'm just trying to give you some of both. I've done a few of the limit comparison test. I want you to make sure on here's the comparison test as well. So, oh, and I should have put for n greater than or equal to 1 in this note right here. Alright, so that's a lot of comparison tests, limit comparison tests, and all that stuff. Now, we're going to get into absolutely convergent, conditionally convergent, or divergent. And so, in terms of what goes on there, if we have the sum of the absolute values of a sub n converges, then this is a scenario what we call absolutely convergent. If you have a sum where a sub n, and by the way, if the absolute value converges, you're going to get the regular series converges as well, because you're just basically taking the negatives out of there, and so you're adding up an even larger number. So versus you're going positive negative in the other case. Okay. In the other case, if you have the sum of the absolute value of the a sub n diverges, but the sum of a sub n converges. Well, in this case, this is called conditionally convergent. And in the case where both of them diverge, we just call it divergent. Okay. So those are the three sort of scenarios that we're gunning for. And what we always start to check with is the sum of the absolute values. Now the nice part about the ratio test and the root test, they will always check for absolute convergence. And what happens if n equals 1, you either have one of two things happening. It's either going to be, well, I should be careful here, not always. If it equals 1, there is a chance though where you could have conditionally convergent, right? So you could also have absolutely convergent in certain cases, and you could also have divergent in certain cases, but it would have to equal 1 in order for the ratio test or the root test, I should say, only, in order for us to have conditional convergence. Okay, that doesn't mean if it equals 1 it's guaranteed conditional convergence. So we can go through scenarios where that happens and where it doesn't happen as well. But so just to get it tricky right out the gate, I gave you one where we'll look to see if this is absolutely convergent, conditionally convergent, or divergent. If we take the absolute value of this song and dance here, notice that just becomes the summation. You get rid of the -1 business. So n equals 1 to infinity of the cube root of n over n cubed plus 7. Okay, so now what do we do? Well, you could try the ratio test. We could have tried that before, but you'll actually run into a problem. I'll tell you right now. You'll have the n plus 1s, kind of similar to what happened before. The n plus 1, the cube root of n plus 1, and the cube root of n, that'll go to 1, and then the n cubed and the n plus 1 cubed, that'll kind of tend towards 1 as well. So at the end of the day, how do we actually approach this then? Well, if that's the case, we'll start trying to look at some of the other tests we have. Well, if you look, we have let me write it this way. If I go n to the 1/3 over n cubed, notice that is the same as 1 over n to the 8/3. Right? So, and we know that the summation n equals 1 to infinity of 1 over n to the 8/3 is a convergent p-series with p equals 8/3. And the reason why is 8/3 is greater than 1. So since, in case you're wondering, since p is greater than 1. Okay, so now we have that. Try and work with this. That means that when we take the limit as n goes to infinity of the cube root of n over n cubed plus 7, and we divide all that by 1 over n to the 8/3, that becomes the limit as n goes to infinity. Notice this is n to the 1/3 and this is n to the 8/3 all over n cubed plus 7. And at the end of the day we get n to the 9/3 because you add the exponents, but n to the 9/3 is just n cubed. So you get limit as n goes to infinity of n cubed over n cubed plus 7. Well, that limit you can just go and take L'Hopital's 3n squared, and then this just becomes 1. But we're using a limit comparison test. So what that tells us is that this sum, notice we were working with the absolute value too. So since this would converge, well, let me write it this way. So first off, the summation n equals 1 to infinity of the cube root of n over n cubed plus 7 is convergent by the limit comparison test. But since that's what is the absolute value, so that means that the summation n equals 1 to infinity of negative 1 to the n of the cube root of n, and then you have over n cubed plus 7, is absolutely convergent. Okay. I hope that makes sense in terms of what's going on, but that's what we're going to be looking at over and over again for those. And so our next one, if we did natural log of n over n, notice if we try to do the absolute value of this, what happens? Well, first off, the negative 1 to the n goes away, and so we get n equals 1 to infinity of just natural log of n over n. Okay, well that's hunky-dory, and we could try and use different things. We could try and use like we could have tried to use the ratio test once again. If you want to see it, I can show you. It's going to be inconclusive as well. So now, natural log of n over n, let's rewrite this. Once again, this probably looks very familiar. We had a natural log of n to the 4th. This will be a little bit simpler though, since we just have an n down below. So this becomes, we could write the first term, when you plug in 1, you get 0 over 1, which is 0. Plug in 2, you get some number less than 1 up top. So we'll write natural log of 2 over 2 plus the summation, and then it gets a little bit nicer after we get n equals 3 to infinity of natural log of n over n. And the reason why we're going to look at that is because natural log of n is greater than 1 for n greater than or equal to 3, and then you have natural log of n over n must be, oops, I don't even need the equal to, but we can leave it in there if need be. You have greater than 1 over n for n greater than or equal to 3. And so the summation n equals 1 to infinity of 1 over n is a divergent harmonic series. Okay, well that's divergent, and so you have a smaller series that's divergent, so the summation n equals 1 to infinity of natural log of n over n is divergent by the comparison test. But the good news here is that does not give us information about the original series. So we have that this is divergent, so the absolute value is divergent, so it's not absolutely convergent. So this tells us at this point it's not absolutely convergent. Okay, so then the next test that we'll check for is the alternating series test. And this will try and see if it's conditionally convergent. Okay. And so in this case, what happens? Well, we have to define Bn, and so Bn is just the positive term, so it's natural log of n over n. And then we have to show it's decreasing 1, and then we have to also show that on top of that we have this has a limit as n goes to infinity of 0. Well, that's not hard for the limit as n goes to infinity. So limit as n goes to infinity of natural log of n over n. We can use L'Hopital's rule. So it becomes 1 over n over 1, which equals 0. So good, we're okay there. Now what we'll do is we'll define a function f of x equals natural log of x over x. And so what happens here? Well, f prime of x, we need to show that this is always negative for n greater than or equal to 1 essentially, but we can even do n greater than or equal to 3, or just find some point where it's decreasing for good. So f prime of x equals, so we get x squared and then x times 1 over x, and then minus, you take the derivative of the bottom, which is 1, times natural log of x. So notice this is 1 minus natural log of x all over x squared. Now if you find, you can go 1 minus natural log of x equals 0, and then you get 1 equals natural log of x, raise e to the both sides, so you get x equals e. So if you have e here, and if this is your x values and this is f prime of x, you have it being 0. Now if you plug in a number less than e, so say 1 for example, notice you get a positive on top, positive on the bottom, so that's positive. So it's increasing up to e, and then anything beyond e, you'll get negative values. So yeah, the part that confuses you, the phrasing absolutely, not absolutely conditionally. So yeah, it's absolutely convergent, meaning think of the absolutely. I don't really toss in the li part. I think of absolute, and the reason why I think of absolute is absolute value, right? So absolutely convergent is talking about absolute value being convergent. That might be a better way for you to kind of think about it in terms of what's going on there. So think about absolute value being convergent. So the absolute value of the terms being convergent, excuse me there. So that's what we're kind of looking for. Versus conditionally, we're just looking for the regular series to be convergent. So the condition where we're just looking for the regular terms with the negatives involved. So this thing's decreasing. So this thing's decreasing for x greater than e, but so for n greater than or equal to 3. So what that tells us, I know I'm running out of room, so this thing converges by the alternating series test. And so what that tells us, since it was not absolutely convergent, but the regular thing converged, this thing is conditionally convergent. So that is our final answer on this one. Hopefully that helped with the phrasing. Absolute, think absolute value. That's the biggest thing. Yeah. So absolutely convergent is talking about the absolute value of the terms leading to a convergent series, versus conditionally we're just talking about the regular series itself. Now, the interesting part, if you have no negatives involved, you're done right away, right? Because absolute convergence and convergence itself coincide. So kind of keep that in mind too. So our next one, this is a little more interesting in terms of finding what this actually becomes. So we have a summation here. We have n equals, let's start at 1 and go to infinity. Okay, let's look at the terms up top and then down below. Notice this first thing I can write as 0.45 over 1 factorial, and then I can write this as 0.45 to the first, because we're trying to catch a pattern here. So first off, it's 0.45, and then over something factorial, right? Okay, so where do we go from here? Well, we want to go 1, 3, 5, 7, and so on and so forth. So notice if I start this thing, the terms go 1, so our n values are 1, 2, 3, and then we have 4, right? But what we want is we want this to be 1, and then when we plug in 2 we get 3, when we plug in 3 we get 5, when we plug in 4 we get 7. Notice that each time this thing is increasing by 2. Okay, so that means we're going to have a 2n of some sort. Well, when you plug in 2n, notice we want to turn 2n into 1. Okay, then we want to turn 2n into 3, then 2n into 5. Well, if I take 1, plug it in, I get 2n, and then that would be 2 here. Then 2n in this case it would be 4. 2n in this case it would be 5. Oh, I'm always 1 off, so what I'll do is I'll just subtract 1 and I actually have the value. So what this is 2n minus 1 factorial, and then I have 2n minus 1 up top here. Okay, now I think we're ready to use a ratio test. I think this is the time. So in terms of the ratio test, so we got a factorial in here. I'm glad to see, hopefully that can help answer your question in terms of how this thing goes. So limit as n goes to infinity of, we want an absolute value of a sub n plus 1 all over, oh, I forgot one big part. I'm sorry. Notice we want -1 to the, what would this be? We go positive then negative, so this would be n minus 1 power. Okay, so limit as n goes to infinity of a sub n plus 1, and then we have all over a sub n. Well, that equals the limit as n goes to infinity. Now, I'll even plug in for the negative right now, but it's not really necessary at the end of the day because you're taking the absolute value, but just so you can see how it works. So a sub n plus 1, you might want to write that down here. Well, first off, actually, I'll write a sub n. That'll be the easier of the two. So a sub n equals, we have, and I'll put the -1 to the n minus 1 first. Then you have 0.45 to the 2n minus 1 all over 2n minus 1 factorial. So that means a sub n plus 1, we're placing every n, and you might want to get in the habit early on, you'll get better at it in time, but replace every n with n plus 1, put it in parentheses though. So, and you'll see why here in a second. If you don't put parentheses around the n plus 1, you'd make a mistake right in that position right there. So, and the same thing down below, you need n plus 1 in parentheses because it's replaced the whole n, and we have that for right now. Okay, so just to simplify the a sub n plus 1 to make our life a little bit easier, this is -1 to the nth power. Now this becomes 2n plus 2 minus 1, so that's going to be 0.45 to the 2n plus 1 power. That's kind of interesting right there. And then on our next bit we'll have 2, this is n plus 2 minus 1, so that'd be 2n plus 1 factorial down below. Yeah, so this is actually a common part where people mess up. When you put in n plus 1, what I would always do, just wherever you see an n, put the n plus 1 in parentheses. Just how I did there. Even though it wasn't necessary for me to do that, like I didn't have to do it right here, but I did. If you get in that habit and you do it every single time, you aren't going to screw it up. That's the main thing, is if you put in parentheses n plus 1 every time wherever you see an n, right? And so all I did is here's an n, here's an n, and here's an n, and I just put n plus 1 in parentheses every single time, and it's going to work all the time. Okay, so you'll actually have that set up nicely for yourself. Now we actually have to start to plug this business in, so we get -1 to the n, 0.5 to the 2n plus 1 is a simplified format. Then we have a 2n plus 1 factorial. And then what else do we have? We have a 0.45, okay, yeah, -1 to the n minus 1. And we have a 0.45 to the 2n minus 1 over 2n minus 1 factorial. A lot of stuff going on there, right? But the -1 to the n minus 1, you have -1 to the n, and so this will cross off. All you're left with is a -1. Okay, and then we'll line up this stuff so the rest looks pretty nice in terms of what goes on there. So the reason why I messed around with the -1, you can break this up into different absolute values since they're all going to work out to be positive. So limit as n goes to infinity of -1, the absolute value of that. Let's group the 0.45s together. So you get 0.45 to the 2n plus 1 all over 0.45 to the 2n minus 1. And then last but certainly not least, another absolute value. We have the 2n minus 1 factorial goes up top, and the 2n plus 1 factorial goes down below. Yeah, I agree. These do look nasty. You will handle enough of them. That's my idea in terms of, you'll have plenty of homework problems. If not in this section, don't worry. When you get to power series, they come up quite a bit, and you get more comfortable with them. So the -1, that's just +1, so that's not going to make a difference here. Okay, so you see the 0.45. You have 2n plus 1 and a 2n minus 1. Here's an easy way to handle that. Okay. In terms of that, you can just take this absolute value, and then you can subtract the exponents because this is a constant. So this goes 2n plus 1 minus, put it in parentheses, 2n minus 1. And we'll deal with that in a second. And then in this next one, we talked about this a second ago. The only difference is your 2n minus 1 factorial. Notice that's the smaller of the two values. So if we start with 2n plus 1, what's the term before that? That's my question here. So what's the term before 2n plus 1? And actually, I see the stream's having problems. So what I'm going to do, I'm going to pause the video. I'll give you 5 minutes. I'll have you try and figure this out, and we'll come back at this point. Okay?